Hello, welcome. I am Suresh from Institute of Aeronautical Engineering, Dundigal, Hyderabad. In today's topic, we discuss about height measurement from aerial photograph. Height measurement from aerial photograph in today's topic. Actually, what is an aerial photograph and how to measure the height of an object from aerial photograph? What is aerial photogrammetry? So here you can see some airborne vehicles. So we capture the photograph using airborne vehicle is called aerial photogrammetry. So aerial photogrammetry is the taking a photograph from an aircraft or any other flying objects by taking to 60 to 70% of side overlap and 20 to 40% of end overlap. Okay, so this is side overlap and this will be your end overlap values. So aerial photogrammetry is a method of photogrammetry where we capture photographs using airborne vehicles by overlapping 60 to 70% of previous image in side overlap and 20 to 40% of previous image in end overlap, right? This is called aerial photogrammetry. So in aerial photogrammetry, I can measure objects or such as building height or tower height in aerial photogrammetry by process called stereoscopy and 3D view. So by process called stereoscopy, I can measure the parallax as well as I can measure the elevation of an object in vertical photograph. So there are various platforms of aerial photogrammetry which includes fixed wing aircraft, you can see here, helicopters, unmanned aerial vehicles, so UAV vehicles or drones we are calling. So UAV vehicles, in DRDO we have a UAV vehicle called Rustam 2. Okay, Rustam 2 is an unmanned aerial vehicle launched by DRDO. Okay, and balloons, rockets, kites, and parachutes. So these are the various sources of elements which can capture an aerial photograph from atmosphere, which helps in photogrammetrical surveying. Geometry types of aerial photograph. So actually, when you are capturing an image, that image may be either vertical capture or oblique. Okay, so when I capturing image, I will use a camera. Based upon the camera and axis of the camera, we are calling as vertical or oblique photograph. So you can see a plumb line here, or you can see camera axis or principal axis. This is called a principal axis. If this principal axis is exactly vertical to the ground, we are calling as vertical photograph. If principal axis has been inclined with camera axis at an angle of 30 degree, we are calling as low oblique photograph. If principal axis has been inclined from plumb line at an angle of 60 degree, we are calling as high oblique photograph. So we are taking the principal axis and plumb line. So if principal axis is inclined more than 30 degree, we are calling as low oblique. If it is inclined more than 60 degree, we are calling as high oblique photograph from plumb line or camera axis, right? So if you observe this figure here, the vertical axis or vertical aerial photograph camera tilt is less than 3 degree from vertical. So we have to see tilt also. So if camera axis tilted less than 3 degree, why? Because if you observe this figure, you can see aircraft here and the camera is just placed at the bottom of the aircraft somewhere here. So this will capture some figure like this. We can get a 4D view like this. So this is nothing but this is the image what it represents. Okay, if you capture any image like this from vertical aerial photograph, we can get a this image or this image. Okay, so when I'm capturing an image using airborne vehicle, okay, I'm capturing image using airborne vehicle. So this aircraft will not stand in position balanced. Yes, it is unbalanced in atmosphere because of various forces. So there is a dragging force acting, gravitational force is acting on that, wind pressure is acting, thunderstorms are acting, many sources of factors which affect the fly of the aircraft. So aircraft cannot fly smoothly in atmosphere. So there are various factors which governs the vertical photograph. So some factors will cause tilt in the aircraft. So if aircraft is tilted, the camera is also tilted. So like helicopter, the aircraft cannot be well balanced. So if the camera axis is tilted, if the camera is tilted less than 3 degree and the photograph is captured, that is the plumb line is vertical and principal axis is 90 degrees. Okay, so either this or this we call as a vertical photograph. Okay, if we satisfy both the equation, then we call as a vertical photograph. If camera inclination is about 30 degree from vertical, or if the camera tilt is more than 3 degree, if tilt of camera is more than 3 degree and camera inclined about 30 degree from the vertical line, it's called low oblique photograph. If camera inclined about 60 degree from the vertical, we call high oblique photograph. If you see the figure here, this camera axis is there, is a plumb line. If the camera axis is inclined more than 60 degree from plumb line, is called high oblique photograph. If the camera axis is inclined more than 30 degree from plumb line, we call as a low oblique photograph, right? So now, if you are capturing any image, that image may be vertical, it may be oblique, or it may be high oblique or low oblique, or even tilted. So suppose I'll give an example like this. So there is my aircraft. I've captured image, this principal axis. So there is a building here. In vertical measurement of aerial photogrammetry, what we discuss. So I have captured the image like this. This is my vertical. Okay, I found radial distance RB here. I found one radial radius RR here. Okay, and I want to extract the height of this object or building, whatever it is. So when I am capturing vertical image, one ray is focusing at the top of the building A, and one ray is focusing bottom of the building B. So here angle is theta, here angle is theta. This is called RB, this is called RR. Now how to extract the height of this tower in vertical aerial photogrammetry is the concept for today's class. So we are discussing about that particular method in stereoscopy, how we do this. So as we discussed the 60% overlap and 30% overlap, you can see here, this is end lap, which is 60 to 70% overlap. This is side lap, this is 20 to 40% overlap. Okay, so in aerial photogrammetry is method of photogrammetry where we can capture the photographs by overlapping 60 to 70% of previous image. In side overlap, we overlap 60 to 70% previous image. In end overlap, we overlap by 20 to 40%. You can see here, this is an end overlap, this is also an end overlap. Whereas this is side overlap and this is also side overlap. So here we overlapping two images like this. We overlap like this, okay? We overlap like this. So you can see image here. So we overlap 60 to 70% of previous images like this. Okay, so most vertical photographs are taken with frame cameras along flight line. Now what is flight line? A series of exposure stations. You can see here 1, 2, 3, 4, 5, 6 stations are there. So a line connecting all the exposure stations in atmosphere is called flight line or flying line. So most vertical aerial photographs are taken with frame cameras along flight line. The line traced on the ground directly beneath the aircraft during acquisition of photogrammetry is called nadir line. So this is a flight line, and the line is parallel on the ground is called nadir line. Okay, nadir point, nothing but a point on the ground. The central point of the photograph on the ground is called ground nadir point. The center point in the photograph is called photo principal point or photo nadir point. The center point in the photograph is called photo nadir point, and the center point on the ground from photograph is called ground nadir point. So if you connect all the ground nadir points, there is center of the photograph. So these ground nadir point and the flying line are parallel to each other, right? This line connects the images center of the vertical photograph. So each vertical aerial photograph overlaps the next photograph in the flight line by approximately 60% or 70%, and side overlap by 20 to 40% as we discussed here. This overlap is very important because It provides at least 2 or sometimes 3 photogrammetric views of each object in the real world along the flight line. So, how the overlap can be done? Okay, can I overlap according to my wish? No, it's wrong. So when we are taking, suppose this is an image which have been overlapped from atmosphere, I have fiducial marks. So these are present at the edges of the photograph. These are called fiducial marks. These are called fiducial marks. So when I am taking the 60 to 70% overlap, okay, when I want to overlap the 60 to 70% of the overlap, this is the first image I have captured from atmosphere like this. Okay, again from here I'm going to capture the second image. So I should overlap the previous image by 60 to 70% only. Okay, from here again I will overlap this. Right, again I go for next station, again I get some fiducial marks here. Again from here I will overlap the 60% of the previous image like this. So when I get a series of, again I get the principal point here. This principal line and this flight line both are parallel to each other. These principal lines which connect on the ground are called ground nadir points, and this is called nadir line. So this ground nadir line and the flight line both are parallel to each other. Next, if you go for the geometry of vertical aerial photograph, as I discussed, we can see the fiducial marks, mission ID, frame number, date of the photograph, and nadir point and principal point. So we need to focus about these elements in vertical aerial photograph. So what are the fiducial marks? So these fiducial marks are called spatial reference points. These fiducial marks are called spatial reference points. So these are called spatial reference points. Why? Because when I'm capturing a photograph from atmosphere, I should recognize these points at least as a reference point, because there may be some tilting of the aircraft. I should bisect these points. I should bisect these points if I want to capture the next image. So from here I'll take 60% of this photograph. I'll capture the next image like this. Again I have these points here. I will take 60% of these and I will capture the next image like this. Okay. For this purpose only, I take the fiducial marks. These are called spatial reference points. So these are very important in your aerial photogrammetrical survey, right? And data photogrammetry and photo nadir point and principal point. So we can see 2 points here. One is principal point and photo nadir point. So the point, I mean the intersection of all the nadir points. So if you intersect these two and these two nadir points, or if you intersect these corners and these corner edges also. So the intersection of all the fiducial marks, intersection of all the fiducial marks is called your principal point, PP. Okay, in aerial photogrammetry, the center point is called PP, principal point, where all the fiducial marks intersect in aerial photograph. This is called principal point. And nadir point. What is nadir point? A point which is passing from principal point in photograph and touching the ground. So if you observe, this is the principal point, this is the nadir point. A line passing from principal point and touching the ground is called nadir point. So this is called ground nadir point. And here we call principal point, and it is also called as photo nadir point. I mean this is a photo, this is called principal point. So these are the fiducial marks, principal point, photo nadir point, and this is the ground nadir point. Okay, this is the ground nadir point, this is the photo nadir point, this is the principal point, right? And here we will discuss the exposure station. So this, as I said, that exposure there is nothing but the point in atmosphere at which we capture the image. A point in atmosphere where we capture the image is called exposure station. This is called exposure station. Suppose in next I have captured image at this point. This is exposure station 2. If this is 1, this is 2. Again, at some interval I have captured the point here. This is exposure station 3. If I join all the exposure stations, I'll get the flying line. And if I join all the nadir points on the ground, here one nadir point, here one nadir point, and here also one nadir point. So if I join all the nadir points, this is called nadir line. So flying line and nadir line are always parallel to each other. Okay, wherever you get the exposure station, you get the ground nadir point, and whenever you connect the exposure stations, you will get the ground nadir lines. Right? Here we have in aerial photogrammetry in elements, we have a negative, we have a positive, exposure station, optical axis or plumb line. So geometry and components of vertical aerial photograph. So these are the components and geometry of a vertical aerial photograph, and fiducial mark, nadir point, principal point. Okay, so mission ID, frame number. These are the basic elements of your vertical aerial photograph. Now this is your method 1, how to measure an height of an object. So there are few methods are there. Height measurement of aerial photograph by relief displacement. This is F. Height measurement of aerial photograph by relief displacement. If you observe this tower in the photograph, we can find 2 points. One point at the bottom, one point of the top. So in vertical photograph, I want to find the height of this building. Okay, I know the width, I know the length of the building, but I want to find the height of the building like this. Here also can find some point like this. I can see the 3 corners of the building, I cannot find the 4th corner of the building. I can find the 3 corners. Here also I can find the 2 corners, I will find the 2 corners, but I can't find this corner. Okay, I can't find this corner. I can find the 3 corners, I can find the length and width of the building also. Right? So how I can extract this height of the tower or object or building using relief displacement. Okay, so in vertical aerial photogrammetry, if you want to speak truly, in vertical aerial photogrammetry, we get exactly the top view of land. So if suppose this is an, I'll call this as a low oblique photograph. I'll call as a low oblique photograph, not an high oblique photograph. Displacement. So displacement is shift of the location. Shifting the location of an object in a photo is called relief displacement. Displacement is the shift in the location of an object. Okay, in photo, which does not change the perspective characters of photo. So if when I captured a photo from atmosphere, I have get an image like this. I want to find the height of the building. So how I can find the height of the building? Okay, so we have various methods are there. So I will derive an equation for relief displacement, height measurement of aerial photograph through relief displacement. So if you observe a figure like this, suppose take this building, I want to find the height of this building. Okay, I want to find the height of this building. So this is my plumb line. For distance of capital D, I have a building here. I want to extract the height of the building is H. This is A. This point is B. So I have focused at the bottom of the building. One ray is the bottom, one ray is the top of the building. Similarly, from aircraft, I have get one ray here, one ray here. This is my straight line. Okay, imagine like this. So this is RB and this will be your RR. So this is here, this will be. This is B, this will be A. So bottom is A and top is B. It also AB. So I'm calling the distance as RB and the complete as RR. Okay, and from at some distance, this is from here to here I'm calling as F, and from top to bottom I'm calling as capital H, height, flying height H. Okay. Okay. From this equation, okay, from the equation I can write like this. This distance is RB by D is equal to F by H. I can write as RB by D is equal to F by H. These two are similar triangles. So if I take a triangle like this, RB by D is equal to, this is RB, this is D. RB by D is equal to F by H. And I can write like this, RR by D is equal to F by H minus H. RR complete. RR by D is equal to F by H minus this small h. Okay, these are the two equations. From here I can write like this: D is equal to, for first equation, D is equal to HRB by F. Second equation I can write like this: D is equal to RR into H minus H by F. RR into, so I got the equation that RB by, I can write like this: RB by D is equal to F by H, for previous figure. So I can write RR by D is equal to F by H minus H. Now I can write D is equal to, for first case, D is equal to HRB by F. For second case, D is equal to H minus H into RR by F. So if I equate this 1 and 2, I'll get that HRB by F, HRB by F is equal to H into HRB by F is equal to, what is the D equation is, RR by D is equal to F by H minus H. So H minus H RR by F. If I equate 1 and 2, if F is cancelled, so HRB is equal to HRR minus HRR, right? I write like this: therefore HRR minus HRB is equal to plus HRR, small HRR, plus HRR. If I remove H common, RR minus RB is equal to HRR. I want height. H is the height of the building. So from here, H is equal to H into RR minus RB by RR. So therefore H is equal to H into delta R by RR is your formula. So H is equal to H delta R by RR is the formula for relief displacement, right? So there are various causes for relief displacement. Okay, let us focus on causes of relief displacement also. Okay, so there are various causes for relief displacement. So far we are aware of what is relief displacement, right? So they have a formula H into delta R by RR. Delta R is equal to RR minus RB. This is your clear. Now the amount of relief displacement depends upon 5 factors. One is height of the object, focal length, height of the object from your radar point, okay, elevation from the photograph. There are various factors are there. Let us discuss each factor in detail. How a relief displacement causes of relief displacement. So if you see here, height of the object. So for height of the object for AB is more than compared to CD. So if you take AB here relief displacement is more compared to AB than CD. See here, when the distance of the object from the radar point remains same, but the object height increases or decreases, higher object is more displaced. Okay, so higher object is more displaced. If you see the height of the object, but the object height is increased or decreased, higher object is more displaced in relief. Okay, so if object is low, the relief displacement is also minimum. If object is high, displacement is high. If you take this figure, here height is less than compared to here height. So this height is H, this height is H1. Suppose this have more relief displacement than compared to this height, right? So height of the object also plays a role in your relief displacement. Next, second one is distance of object from nadir point. So this is a point on the ground, this is called ground nadir point, and distance, see here, as I'm moving far distance, I have far deflection angle or deflection radius. As I'm moving very, if the point is height is very close to radar, we have very less thing. So I can take like this is RB and this is RR. Here you can take this is RB and this is RR. Okay, how it is RR. So you can see here, as the height distance is more, the RR rate is more. The distance is small, the RR is small from the nadir point. So these are various factors which cause relief displacement. You can see the first half of the figure, or you can go for the second half of the figure. If I close this part, if I close left part or right part, you can see the clear view. In this also, height of the object. See here, if the height of the object is more, this is RB and this complete is RR. Compared to this is RB and RR is less. Because height of the object is less, RR is less. Height of the object is more, RR is also more. So it depends upon several factors like this. So based upon the height of the object or position of the object from ground needle point or focal length. Next one is focal length. When the focal length of the camera lens is increased, the relief displacement will be more. On the other hand, when the focal length of camera length is decreased, the relief displacement is less. So based upon the focal length also it happens. So if it is focal length is more, displacement is more. Focal length is less, displacement is also less. So these are the one of the factors which govern the relief displacement. And next one is flying height or altitude. So you can see the figure here. If the focal length of the camera lens remains constant, when the flying height increases, relief displacement decreases. See here, if the height increases, displacement is very less. If the height decreases, displacement is very more. RR, RB, RB, RR. You can see here in these two things. You can see as the height increases, displacement is decreases. So the it is less when compared to, you see the angle here. The angle is here. Okay. As height increases, displacement decreases. As height decreases, displacement increases. This is one of the example for your relief displacement cause and height of the object in relation to datum plane. Okay, see here data height of the object CD. Okay, you can cover this. See height of the object in relation to displacement RR, RB. Here also RR, RB. So here displacement is more than compared to this figure. Okay, so there are various factors which govern the relief displacement. Effect of the field of view. So if the normal angle of view will result smaller relief displacement and higher angle of view result higher relief displacement. So if the normal angle of view will cause smaller relief displacement. Okay, so normal angle of view will cause smaller relief displacement. You can see here this is vertical RR, RB. So normal angle of view cause relief displacement is very small, whereas higher angle of view you can see with this with horizontal, with vertical RR, RB. So there is more relief radial radius than compared to here. Here we have more radial radius when compared to this low radial radius. So like that, there are the 5 factors which governs the relief displacement. Okay, now height measurement from relief displacement. So given derivation that we have derivation that h delta r by rr. So small h is equal to capital H delta r by rr, where delta r is equal to rr minus rb. This is the formula which we have derived previously. But apart from this, we have many authors who have derived the equation, right? So formula is h by h is equal to d by r, or h is equal to d into h by r, or d is equal to r into h by h. So we can use any of the formula to find the relief displacement. Okay. If you want to find height of this building, we can use any of this formula, or we can use this formula also. What I have said, h into delta r by rr. Small h is equal to capital H into delta r by rr. We can use this formula also. Next, measurement of height measurement based on shadow length. So this is based on vertical aerial photograph, and this is based upon shadow length. So when you compare this method with this method is not accurate, whereas this method is accurate. Okay, why? Because in photograph we are measuring the height of the object, Whereas based upon the shadow length, we are measuring the height of the object. So at 12 o'clock, I can find the shadow up to here only. This is not there. But at 4 o'clock, 4 p.m., I can find the shadow length more compared to the 12 o'clock shadow length. At some 6 p.m., it will be more than the compared to the previous shadow length. So we can capture the height of the object using shadow length also. So suppose you can take this. This is a building here. Building have a shadow here. This length is called L. This is the height of the building H. And from sunlight, it makes an angle of theta with horizontal. Okay, this shadow makes an angle of theta with horizontal towards the sun rays. If you take tan theta in this figure, tan theta is equal to adjacent by hypotenuse, opposite by adjacent. So opposite is L, but adjacent is H. From here I want H. H is equal to L tan theta. I want H. H is equal to L tan theta is the formula. So that is very basic formula where we can extract the height of the object based upon the shadow length. But the shadow length will differ from time to time and the height may not be exact because shadow is sometimes short, sometimes shadow will be long based upon the morning and evening times. So from here I can find the H is equal to L tan theta tan E. So if my height of the object is, if my length of the building shadow is 20 meter or 20 feet and angle is 30 degree, then my height of the building is 11.547 feet. Okay, this is how we can measure the height of the object using relief displacement method or using shadow method, and computation of building height using stereoscopic parallax. So in photogrammetry, we have various methods. We have three methods: method 1, method 2, method 3. Method 1 is using relief displacement formula. Method 2 using your shadow length formula, and method 3 using stereoscopic parallax. Now what is parallax? Is the apparent displacement in the position of an object. Now what is stereoscopic parallax? The same image have been obtained from two different elevations. We get a stereoscopic parallax. Suppose I have captured an image from 2000 feet height and I capture the same image from 2500 feet height. So I have captured the same image from two different elevations. I get a stereoscopic parallax. So parallax is caused by taking the photograph of the same object but from different point of elevation or observation. It's called stereoscopic parallax. So there are two different types. One differential parallax, one is absolute parallax. So what is differential parallax and what is absolute parallax? So in differential parallax, we'll see the difference between the top and bottom of the building. You can go for the differential parallax. I'm calling as DP here. Okay. The same image I have captured from two different elevations, or the same image captured from two different elevations. You can see here there are some buildings. This is the top of the building, this is the bottom of the building, this is top of the building, bottom of the building. Sorry. So this is the same image but from different elevations. Okay. So here I can see top and bottom also. So if I want to extract the differential parallax, difference between the stereoscopic parallax at the top and base of the object. Difference between the stereoscopic parallax at the top and base of the object is called differential parallax. If you observe a tree here and figure 1 in figure 2. So the top difference is 13.5 mm and the bottom difference is 15.2 mm. So 15.2 minus 13.5 mm is 1.7 mm is your differential parallax value. Okay, so 1.7 is the differential parallax value of your differential parallax. So like that, how we can extract the height difference between two objects. So these two images have been captured from two different cameras from same elevation. Okay, so this is the left side view, this is the right side view, and the right side camera placing on the right side. This is a camera placing on the left side, but the two images have been overlapped. So when we take the top and bottom difference of the object, we can extract the differential parallax value. Now, absolute stereoscopic parallax. So differential parallax dp formula is nothing but difference between the top width and bottom width, or bottom width minus top width. This is the formula for a differential parallax. We have two widths, bottom width minus top width. You can see the figure here. Bottom width minus top width, we get the differential with parallax. And absolute stereoscopic parallax. So it's the average distance between PP and CPP. So the average difference. Okay. What is PP? Is a principal point or a center point in the photograph. It's called your PP. So the difference between the average distance between PP and CPP is called absolute stereoscopic parallax. So PP is called principal point or center point in the photograph, and CPP is the conjugate principal point or adjacent photos principal point. CPP is this is called CPP. Adjacent principal photo point or adjacent photos or conjugate principal photo point is called CPP, and PP is the principal point. So the average distance between this PP and the CPP, the average distance between this PP, suppose it is 20 by 2, 10, is called absolute stereoscopic parallax, or between CPP, this is 10 by 2 is 5. So like that, the average distance between PP and CPP is called your absolute stereoscopic parallax. Next, computing height using stereoscopic parallax. So how we can extract the height of an object? So we found the differential parallax we have found. We found the differential parallax, that is dp we have extracted. Now we are going to find the height of an object using stereoscopic parallax. Now in differential, dp is the bottom width minus top width. That is p1 minus p2 will give your dp, differential parallax. But we are going to find the height of an object using stereoscopic parallax, not using relief displacement. Relief displacement height formula is different. That is h is equal to h into delta r by rr. Finished. This is using stereoscopic parallax for relief displacement, but this is using stereoscopic parallax. So we have a formula h into dp by b plus dp. Okay. So computing height using stereoscopic parallax, we have a formula that is h dp by h into dp by b plus dp. The formula h dp by b plus dp. This dp formula we know that is, what is formula for dp? Bottom width minus top width. Yes. So dp formula is p1 minus p2, and b is the photo base length, that is b1 plus b2 by 2. Okay. Height of the object is h is equal to h into dp by b plus dp. So here dp is equal to p1 minus p2. That is bottom width minus top width of the tower. Difference between the bottom width and top width of the tower is called your differential parallax. So if you substitute all these fundamentals in this formula, that is h dp by b plus dp, we get your computing height using stereoscopic parallax. Thank you. That's the end for today's class. So far we discussed the vertical elements in aerial photogrammetry survey. So we have discussed how we can extract the height of the object using shadow method, using parallax, using stereoscopic methods. Right? Thank you. Thank you for watching.
Like, share and subscribe. Hit the bell icon for more updates.